4 lectures on linear time verification. The course is carefully designed to make you all unhappy. So some of you have a good background on verification already, others not so much. So the first part of the course will be basic, and the people with a background on verification will be unhappy. And the second part will be advanced, and people with no background will be unhappy, and at the end we will all be unhappy. So that's wonderful, right? Okay, so
always eventually unhappy.
Exactly, right. So in linear time verification, the core idea is that we are going to say that the behavior of a system is a set of sequences. Okay, so we consider that systems that are producing events, and a possible behavior of a system is a sequence of events, and the behavior, the system itself, is going to be described by its sequence of executions. Okay, so that's the core idea. And what happens when you have then a set of sequences as behaviors? That actually what you can say is the behavior of a system is a language. It's a formal language, right, over some alphabet that will be appropriate. And then the second key idea that behind this course is that we are going to reduce, the problem of deciding whether an implementation of a system satisfies the specification to a language inclusion problem, whether the set of behaviors of the system is included in the set of behaviors that we consider adequate. That's the specification, right? And we are going to use automata theoretic techniques in order to solve that problem. So actually the first 2 lectures are going to assume that you know a little bit about finite automata. So I am assuming that everybody here has taken some course about finite automata at some point in your life. Is that true? Who took one? Somewhere, right? Okay, good. So you all know what finite automata are, and we are going to use the knowledge that we all know, for instance, also what regular expressions are, and we are going to use this knowledge in order to construct verification algorithms. Good. So we are going to see a lot of stuff again that Orna has already presented. So that's good for those of you who saw those things for the first time. You're going to see them again, but now from a different angle, right? So let's start with a tiny program, and consider that x and y are Boolean variables. So it's a program with 2 Boolean variables, right? And we are going to describe which is for us the behavior of this program. So let's first define what is a configuration. It's going to be a triple of numbers. First, we are going to say where we are. We are in line, we are going to execute next line 2 or 3 or 4 or 5, and then we are going to give the values of the variables, right? So immediately you can see that we have at most 5 times 2 for values of x times 2, 20 possible configurations that we can have in this program, okay? So what is going to be an initial configuration for us? The configuration where we are here. So there are going to be 4 possible initial configurations depending on the values of x and y. Right? And we want to examine the behaviors of the program for all those possible initial configurations. And let's say that something, a sequence of configurations, let's call that a potential execution. It may not be a real execution of the program. Maybe the program is not able to generate or to go through this sequence of configurations, but we call that just a potential execution, because who knows, maybe if you only know that the configurations are like this, and you don't know the program, it might be something that the program might do, right? So for instance, this would be a potential execution of length 2. And notice also that I am not telling you that the executions have to be full, have to go to the termination point. Just some initial sequence of configurations could be also a potential execution. Okay, so in particular, for instance, this one does not correspond to the semantics of the program, because if you start here with the values of x and y equals to 1, you will not jump here, okay, to line 4. But it doesn't matter, we consider it a potential execution. Good, so then we say which are the executions. The executions are the potential executions which start at an initial configuration and where each configuration is followed by its legal successor, right, by the one that you would have according to the semantics. And here you have a couple of examples. For instance, if you start at 1, 1, 1, then, well, since x is equal to 1, you will enter the loop, and then since y is equal to 1, you will reach this point, right? We are then here, still with values 1, 1, and then you will execute the assignment, you will set x to 0 and move to line 4, and so on, right? Good. So now the idea is that we are looking at the implementation of the system. In this case, this is our program, right, as a set of executions. Okay, there can be infinitely many executions. In fact, in this program, as we will see in a moment, there are infinitely many executions, but it is just a set of executions.
But are executions finite or infinite or both?
For the moment, they are finite. Okay, they are finite sequences. Good. So what is then for us a specification? A specification is going to be just a subset of the potential executions that satisfy some property, right? So we have some property in mind, and then there are executions, there are potential executions, right, that satisfy that property, and that's our specification. As long as the executions, the real executions of the program are there, we find the program good. Okay? Well, this is what is called a positive specification sometimes, in the sense that we describe which are the things that we consider good, which are the executions, the potential executions that are good for us. And you can also describe the specification negatively. That's probably more common, right? What you describe is the dangerous things, the executions, the potential executions that are not acceptable. Okay? And that's another set that will be essentially the complement of that set, right? And it will be a set V. So then the implementation satisfies the specification if you have given a positive specification, then it is the case if the set of executions is included in the set of good potential executions, right? Or if you have given a negative specification, then that's the case if the intersection of these two sets is empty. Okay? Good. So then the idea is that if these two sets, they are regular languages, right? Then we are going to be able to use automata theory in order to solve these problems, right? So assume that then you have automata, right? Finite automata, the ones you saw in your basic course. There is nothing special here. Automata AE and AP for both the sets E and P. Okay, so then you have these two possibilities that you can model the set AP and as a non-deterministic finite automaton, or you can model it as a deterministic finite automaton. And then if you remember your basic course on automata theory, then this check is going to take this time, right? It's going to be linear in the size of the automaton that represents the system, and is representing the executions of the system, and is going to be exponential in the other. But don't worry too much if you don't remember that. It's not going to be very essential. And this inclusion problem actually is known to be p-space complete. Okay, so this exponential here is something that you are not going to expect to avoid in the worst case. Okay, and if the automaton describing the set of potential executions is a deterministic automaton, then maybe you remember that checking inclusion of of whether the set of the language of an automaton is included in the language of a deterministic automaton, this check is going to take only quadratic time on the size of the automata. Okay, and in fact we are going to work more with this approach, right, where you are given a negative specification, and then if the sets are regular, again you can use automata to do the check. Okay, if you are given two automata for AE and for AB, then what I am sure you saw in your basic course on automata theory is that if you are given two automata which accept two languages, say L1 and L2, then it is possible to construct another automaton for the intersection of those two languages, for L1 intersection L2, right? And that if you have these sizes for the automata AE and AB, then the size of the automaton for the intersection is just the product of the sizes. Okay, so you can construct an automaton for this, and then once you have an automaton, how do you check whether the language of that automaton is empty? Well, that's not difficult. You just have to check whether there is some reachable final state, right? And that's something that can be done easily by means of a linear depth first search or something like that. Okay, good. So let's see this in action. So let's take our program. Okay, these are the four initial configurations where we are at line 1, and where the variables x and y have the four possible combinations, right? Now, if you execute the program, you are going to see that, well, if you start with 0, 0, then you are going to jump immediately to the end of the program, so that's it. right? If you start with x equal 1 and y equals 0, the program is going to enter a loop, right? And these are the two things that are going to happen if you have the other two possibilities, right? Good. So this is the state space of the program. Now, how can we obtain from this state space, right, from this graph, how can we obtain a non-deterministic finite automaton which is going to accept the set of executions of the program? Well, that's not very hard. That's it, right? So all you do, well, let's see what has happened here. You know, what we have done is to add first to take these as states of our NFA, right? And we make all of them final states. We have added an initial state. And now, actually, what we have done is to label each transition with the configuration it reaches. Okay, so for instance, this edge going from here to there is labeled with this configuration. We put it there, right? And now it is easy to see, right, that, and we have made all states final. So actually, the language accepted by this automaton is going to be the set of finite executions of the program. Okay? Sorry? As final, right. Because I want to accept not only the terminating executions or the, you know, for instance, here there are no terminating executions, right? So I want to have just all the finite prefixes of all executions. That's my definition of execution right now, right? Also, if you want a partial execution. Okay? Happy with that? Good. Okay, we'll see. It's a good question because we'll see later how this has an influence on things. Anyway, let's start checking some property, right? Let's take an artificial property first to see how this could be done. So imagine that for some reason, an execution would be dangerous if it is a terminating execution, an execution that reaches the final point of the program. This was line 5, right? And such that initially the value of y is 1. At the end, the value of y is 0, and y never increases, right? It's, of course, artificial, right? It doesn't mean anything. It's just to give you a first example. Well, the idea is to construct now an automaton for the set of executions, potential executions. I don't care whether they could be executed or not. For the set of all potential executions that would violate would give you a sequence like this, right? And for that, we can use just regular expressions. Okay, what is the alphabet? Our alphabet is the set of configurations of the program. Okay, so we have as alphabet letters things like 500, 210, and so on. It is a large alphabet, but it is an alphabet. It's a finite one, right? Okay, so then look at this as notation for describing a set of letters, right? This is the set of letters for where you take for L and X all possible values, right? So in the, yeah.
Why do you say that after is finite? Since x, y takes integer values, so we might have...
No, in this program, X and Y are Booleans, right?
We have integer, then
yeah, in the case in which we have integers, that would give you an infinite state space. Yeah. Good. Okay, so let me see. So think of this. Think of this as a short notation for something like, 1, 0, 1, plus 1, 1, 1, plus, okay? So in the usual notation for regular expressions. So then here we have the regular expression describing the potential executions that violate the property. You are saying we start at, even with the potential executions, we don't even require that we start at 1, because you might not even know which is the first line of the program. Doesn't matter. So you say, yes, the only thing I am telling you is that at the beginning, y has the value 1, and then it keeps having the value 1 until at some point it gets the value 0, right? And then you reach the final point. Okay? Everybody happy with that? Yeah.
Do we care about the predicted value of x?
No, we don't care. So this stands for all the letters where L and X take arbitrary values, right? That's the idea. Yeah.
What if y alternates in between the first star and the second star?
No, it doesn't. It cannot, right? What I am saying is a violation is an execution satisfying this, right? where initially y is 1, finally y is 0, and y never increases. Okay, finally means at the final point, at termination, right? When we reach this point. Okay? Okay, more questions? Sorry? That's the cleanest star, right? The cleanest star that you know for regular expressions, right? Okay, so now you probably already know, or all know, right? Or remember from your automata course that if you take a regular expression, then you can immediately construct an NFA, and this will be the NFA, right? So now we have a system NFA, we have a property NFA, and now we can construct the intersection of the two, right? And the intersection is going to be this, but let me tell you a little bit about the coding here so that you understand what's going on. So this is our system NFA, right? And this is our property NFA. And if you remember, the intersection is the states of the automaton for the intersection are pairs of states, one from the system NFA, one from the property NFA, right? Who doesn't remember that? Everybody remembers? Raise your hand if you remember it. Okay, good. So then the idea is we use a color code in order to represent the pair. So we use this color code for the states of this automaton, white, light pink, dark pink, right? And then the idea is this stands for the pair of states where the first element of the pair is the state 101, and the second element of the pair is the light pink state, right? So this is what you get. And then you see that there are no dark pink states there, right? So there is no final state of this automaton. This automaton doesn't have any final state, and therefore when you construct it, you check that it has no final state, and therefore the language of this automaton is empty, and therefore your property holds. Okay? There is no violation. No real execution of the program satisfies this. Okay? Let me tell you, this is of course, these are very, very much toy examples, but in order to give you a little bit more of a feeling what this could be useful for, so imagine this would be some description in some programming language for hardware architectures, right, where you would be describing some circuit here. One of the typical things that you would like to see is whether some gate is actually not doing anything. So for example, here you could ask whether you want, is this instruction really doing anything? And this would mean, is it at some point actually changing the value of y? Okay? So this is something that you can now check using this same idea, right? What you can do is see, ask yourself, is this assignment redundant? Then you describe the potential executions that actually use the assignment, right? And now those are the ones in which, at the beginning, whatever happens, and then you are in front of the assignment with the value of y equals to 0, and then after the assignment, the value of y is 1, or the other way around, right? Okay, so the assignment is redundant if and only if none of these potential executions is a real execution of the program. So now you could do the same. You could transform this into an automaton, you could compute the intersection, and actually you would see that indeed it is redundant, right? So you could remove it after that. And that's something actually that is being done in things that are being done in practice. Okay, so now again, mutual exclusion algorithms are the standard example when you are talking about verification. So this is going to be, look at this as a refined version of what Orna told you, right? And it is going to be a little bit more, it is a kind of second refinement of the one that Orna, the mutual exclusion algorithm that Orna showed you was a very simple one, a very abstract one. This one is a little bit less abstract in the sense that it is an abstract version of Lamport's one-bit algorithm described in that paper. If you ask Leslie Lamport, he will tell you, and I completely agree, what we are going to see is not Lamport's algorithm, Lamport's one-bit algorithm. And why not? Well, the code is perfectly okay. Lamport would say, yes, no problem. This is the code of my algorithm. But Lamport will tell you, but the important thing here, or the important thing when I was dealing with this algorithm, was that, for instance, I am not assuming that this happens atomically. I am not assuming that this assignment happens at just one instant in time. It could be that this assignment starts to happen, and while the assignment is being executed, somebody else reads the variable, right? So we could then model the algorithm in that sense, right? But we are not going to do that, right? We are not going to do that because in that case, the state space would not fit in one slide. Okay, that's the only reason for that. So we are going to assume that these things happen atomically. Of course, then we are simplifying the algorithm, right? We're making our task easier, but, well, that's for expository reasons. Good, then, again, this is the same idea that Orna already explained to you. So we assume that, you know, there is a number of processes 0 to n minus 1, and they communicate through shared variables. So these are Boolean variables, b0 to bn minus 1, all of them initially 0, and a particularity of this algorithm, of this mutual exclusion algorithm, is that the code that the processes are executing is not the same. The code depends on the process. Okay, and as you can see here, so you have here this loop which runs from 0 to I minus 1. So depending on which process you are, this code is going to look different, right? And here also, depending on which process you are, this code is going to look different. Okay, so if you take the case of just two processes, then this is how the code of process number 0 looks like. You just instantiate the template with I equals to 0, and this is how the process with I equals to 1 looks like. Okay, maybe something here, what is this await instruction? This is pseudocode, but this await instruction means you are here until you see that the other process has set, so the value of the variable b1 is not 1, okay, is 0. And the moment that you check that that value is 0, then you are able to enter here the critical section, okay? So actually you can try to understand, it's pretty easy to understand what's happening here. Setting this variable to 1, each process has its, let's say, its own variable, right? b0 or b1, and when when process 0 sets this variable to 1, it is saying, I am interested in entering the critical section, and then what process 0 is doing is waiting until the other one is not interested and then entering, right? And after it leaves the critical section, it says, I am no longer interested. And the process 1 is saying, well, I am interested, and then I wait. If I see that the other one is also interested, then I am very, very polite. I say, I make as if I would not be interested, okay? And then you wait until the other one is not interested, and you iterate this loop. Anyway, this is what you see when you construct the control flow diagrams for these two programs, right? With this notation for the assignments, right? So yet another one. Good. And then you can construct, again, the state of reachable configurations. Now a configuration has 4 parts, because you have to say, where is this process? Is it here or there or there, right? The same for the other process. And then you have to give the variables, the values of the variables b0 and b1, okay? So you could have, in this case, up to 3 times 5, that's 15, times 2 values for b0, 2 values for b1. You could have up to 60 configurations, and out of those, these are the reachable ones, right?
Where do the labels come from on the states?
The labels on the states, I've just given them names, right? Just to say that this is non-critical, this is here. Yeah, they correspond to lines in the program, right? So this corresponds, you know, this would be the non-critical, this would be, actually I'm saying the non-critical, this would be the trying, when you are, so it would be, you would be in the non-critical section when the next thing you are going to execute is this, and you would be trying if the next thing is this, and you would be, right, critical when the next thing is this. Good, okay, so this is what you obtain, and as you can see, it's already a bit larger, right, than the one that Orna showed you. And this would be the system NFA if we would, you know, do the same trick of pulling the configurations here and making all the states final. It would be, we could obtain the system NFA in this way. And then we could check some properties. Now, which are properties that are interesting here? Deadlock freedom, which would be that every configuration has at least one successor. You know, we do not need regular expressions for that. We could do it while constructing this, okay? We could check mutual exclusion, telling that no configuration is of the form B0, B1, C0, C1. right? You don't care about the values of this, but these two should be in their critical sections. We don't need any regular exclusion for that. You know, you could do it just by checking which are the labels of the states you reach, of the configurations you reach, right? Now let's look at the one which is a bit more interesting, which is called bounded overtaking, yeah, for process 0. So the idea is that I would be very pissed off if I just set my variable to 1, saying I am interested in getting into the critical section, and then I say that the other guy gets, let's say, 4 times into the critical section before I get in, right? Because I would say this is unfair. So the property is that the property I want to specify is that after I say I am process 0, after I want to enter the critical section, the other guy should be able to enter at most once. 1 is okay, right? But he could be there before me or whatever. Once is okay, but please not twice, right? Okay, so then, you know, just like Orna said, these are just symbols for sets of configurations. This is the set of configurations where the process I is not interested in getting into the critical section, is outside the critical section. This is where it is trying to enter the critical section. This is where it is in the critical section, right? And this is then the regular expression expressing the violations of bounded overtaking, right? And what you are saying is, well, initially I don't care what happens, but I reach a configuration where process 0 is trying to enter the critical section, and then it continues with configurations where this process does not enter the critical section, right? That's what this means. And then at some point I see that the other process is in. Then I see again that I am not getting in. Then the other process is out. Then I am still not getting in, and then the other process is in again, right? And then I don't care what happens, right? Okay? Everybody happy? Good. So then we could construct an NFA for this. We could intersect it with this, and we could check whether the result is empty. And actually, what you will see, I even have a couple of slides doing this in a little bit more detail. These are the configurations where the process 0 is in the outside the critical section. These are the ones you cannot see it, but these are the ones where you have NC0 there, right? Actually, I think I made a mistake because that's wrong. That one should not be there, sorry. That's NC0, and then we have the ones for T0, and then the ones for C0. This is what Orna also showed you, okay? And then we have these potential executions violating the property, and in fact, if you check it, you will see that the property does not hold. This protocol does not satisfy bounded overtaking. Okay. To be more precise, it's satisfied for process 0, but it does not satisfy it for process 1. Good. In fact, it doesn't even satisfy it for process 0. But this we will see more about that later. Anyway, now the interesting question is, actually there are solutions to the mutual exclusion problem where you have to accept that somebody else can enter several times before you enter. In fact, there is a very nice algorithm due to Don Knuth. It's not very well known, but he published it many, many years ago. And there, it can even be the case that the number of times that a process can enter before you enter can grow even exponentially in the number of processes, right? So you may have to be able to accept that another guy enters 2 times, or 4, or 8, or 16, depending on how many guys are there. But then, probably, as a person specifying the protocol, you are not willing to go into that level of detail. Okay, so do I really want, how many times do I want that the other process enters, right? 732 or 731? Probably your first approach would be to say, what I want to check is that if I am trying to enter the critical section, I will eventually enter it. Yeah, I don't care about how many times the others can enter first, right? So this is what you would call the finite waiting property. If a process is trying to access the critical section, and this means I have set my variable to 1, right? Then I eventually will enter the critical section. And the problem is now, which are the potential executions that violate the property? And we have defined executions as finite words, right? And we have done that because, the automata can deal with finite words. And the problem is that there are no finite violations, right? So if I show you, if you come to me with an execution where you say, look, this I entered, I was trying to enter, and then the other guy entered 422 times, right? I say, oh, don't worry, tomorrow you will enter, right? I mean, it's 425, and then you come with 1,250. Oh, don't worry, tomorrow, yeah. Spanish people like me, we have a lot of experience in that. Telling you, mañana, mañana, right? So the problem is that there is nothing, we cannot specify the property, right? And the only way to specify the violations of the property is to introduce infinite potential executions, right? To deal explicitly with infinite sequences of configurations. So we can formalize it in this way. We can say that the potential executions that violate finite waiting for process I are the infinite words, or omega words in jargon, right, of this shape. If at some point I am trying to enter the critical section, and then I see an infinite sequence. This omega stands for infinite repetition, right? Not finite repetition, like in the Clinic star, but infinite repetition of configurations where I am not in. Okay, so now the problem is, if I want to check this using the same idea, trying to construct an intersection and checking for emptiness, well, how can I do that? I am going to need automata which are able to deal with omega words, right? I have to extend the theory of finite automata to the theory of infinite automata. Well, who knows anything about the theory of infinite automata here? Okay, about 1/2, good. So probably you then already know that this guy was the guy who invented the first model for infinite automata. This is essentially, I think, the only picture we have of this guy. I mean, everybody's showing the same picture, but this was Julius Richard Büchi, a Swiss logician who actually was born in Brazil, but he was of Swiss origin and then worked in the States. And in the 60s, he couldn't care less about verification. He was a logician, and he was interested in other matters. But for those other matters that were important to him, he introduced Büchi, what is called today as Büchi automata. And this was the first model of automata dealing explicitly with infinite words.
He didn't care about verification. The problem was posed by church, who did care about verification.
Okay, did he?
Yeah.
In a certain, okay, yeah, well, yes.
It was about circuits.
Well, yeah, okay, yeah, okay, yeah, fair enough.
I mean, he didn't make tools.
Yeah, it's fair enough. Okay, so first thing, notice that actually this is a complete revolution. When you look at finite automata, the mental image you have in mind is, okay, this is a machine, an abstract machine. It's a machine that gets an input, in this case a sequence, and then gives an output. Yes, I like this word. No, I don't like this word. An infinite automaton doesn't make much sense as a machine, right? Because actually it runs forever. You are never going to get an answer in finite time, right? But it makes perfect sense as a set. I like to look at it as a data structure. It is nothing else but a finite representation of a set of infinite sequences. Okay? And that's what data structures are. Finite representations of things. In this case, it's an infinite set, but great, right? If I can find a finite representation of some infinite sets of even infinite sequences. Good. So what is a Büchi automaton? It has exactly the same syntax as DFAs and NFAs. Nothing changes. You have states, transitions, initial states, final states, right? But the run of a Büchi automaton on a word, now the input is an infinite word, so the automaton is going to run forever on that word, right? So a run is an infinite sequence of states and transitions. And now this is the key issue, that the idea that Büchi came up with is to say, well, let's say that the run is accepting, right, if it visits the set of final states infinitely often. Okay? And then it doesn't make really to speak about final states. They are no longer final. Nothing stops there, right? So actually, when in the context of infinite of omega automata, typically you speak about the accepting states, right? Yes, in order to avoid this idea of final. And then a deterministic Büchi automaton or a non-deterministic Büchi automaton accepts a word if it has an accepting run on it, and you define the omega language, right? Good. It's not very difficult to see that you can generalize the condition, the accepting condition introduced by Buchy a little bit. So you can consider positive Boolean combination of conditions of the form, this set of states must be visited infinitely often. So for instance, imagine we could, using a little bit of notation, we could describe the accepting condition of this kind of generalized Buchy automaton like this. This is a set of states. This is another set of states. This is another set of states. And I am telling you then a run is accepting if and only if you visit this set of states infinitely often, and you visit either this set of states or that set of states infinitely often. Okay? And it's not, yeah. No, visiting a state means visiting one of the, so visiting a state is like you say visiting Israel. Doesn't mean that you have to visit every city in Israel, you just have to visit some city in Israel, right? If you have visited Jerusalem infinitely often, that counts as having visited Israel infinitely often. Okay? Good? So here you have a couple of examples for those of you.
Positive combination. You can define for different combination.
Yes, okay, maybe what I should say a little bit, to be a bit more explicit, is that if I give you an automaton with a condition like this, it is not difficult to construct an equivalent automaton accepting the same language, but with the original condition due to Buchy, right? Which would be only just, G1 and nothing, only one single set of final states. Okay? So we will see maybe a little bit more about that later. But for the moment, just believe it. Okay? So it's not complicated to do that. Good. So here you have a couple of examples. So how many of you are able to say, our alphabet is A and B? And how many of you are able to say which is the language of omega words accepted by this Buchy automaton? Okay. Somebody want to try? Who was the person most at the back who raised his hand? Raise your hand. Now nobody raises their hand, right? So raise your hand again. I saw at least somebody in the third row. No, Bert, you don't count. Somebody else? Yeah, please. Sorry? B star A plus. Well, probably you mean here A omega, right? Because A plus, this would be the notation of regular expressions. And actually, it is a language of infinite words, right? So we have to use a notation for infinite words. So we can write something like this. And this would be the set of all words where you can see B's at the beginning, and then from some moment on, you only see A's, right? Okay, who is happy with this? Who isn't? Okay, so somebody who raised his hand, please. Correct? Exactly. It's the language of all words with infinitely many A's. Anybody can give an argument why that's the case? The problem is always you have to show every word with infinitely many A's is accepted, and every word which is accepted contains infinitely many A's, right? So one of the two halves at least, yeah?
Every time you see A, you reach the accepting state. So if you see A infinitely often, you will see A.
Exactly. Every time you see an A, you go here. So if there are infinitely many A's in the word, you will visit this state infinitely often. For the other direction, yeah.
The only way to get to an accepting state is to either A. So
Exactly. Okay, everybody got that? The only way to reach the final state is with an A. So if you visit the state infinitely often, you must have seen infinitely many A's, right? Okay, what about this one? These are standard, right? Probably, so the people who have seen Buchy automata probably know all of them, right? Finitely many A's, right? So notice that this automaton is deterministic, this one is non-deterministic, right? And the idea is that if we want to visit this state infinitely often, at some point we will have to take this transition, and from that moment on you will only see B's, right? Good. What about this one? Let's make it, this one you haven't seen, right? This one is kind of the simplest one that nobody has seen in a basic course on Buchy automata. Yeah.
After an A, I eventually always see.
After an A, I will eventually see a B. Okay. It is so after an A. So after an A, eventually B. What about the C's? There are C's around. Well, but you can answer. You can, for instance, accept infinitely many C's. Okay. So you don't care about that, right? Okay. So yes, exactly that would be the idea, right? That after you see it, no, but notice that, right? No, that's fine. Yeah, exactly. No, it was exactly correct. Yeah. So after every A, you will eventually see a B later, and you don't care about the C's. So in particular, if you don't see any A's, any A's or B's, that's also fine. Okay. Good. And this is an example of an automaton with one of these conditions, of the form G1 and G2. So you have to visit this set infinitely often, and you also have to visit this set infinitely often. So you have to visit both states infinitely often, right? So which is the language? Sorry? Almost? All the words. Not really, no. You have to visit, for instance, B omega, sorry. You won't accept because B omega visits this one infinitely often, but it visits this one only finitely often, right? Actually, 0 times. Sorry? Maybe I heard somebody from there? No? Mistake? A mistake? Or okay. Good. So then somebody else, maybe you, that didn't. Who didn't. Sigma star A, sigma star B to the omega. This one. This one. Yeah, it is the one where you see, you can use the same argument that we were using here. So because of this state, you have to see infinitely many A's. And because of that state, you have to see infinitely many B's, right? Actually, sorry about that. Oh, probably this was I should have, this was probably misleading you, right? I'm sorry about that. I should have erased that double circle. Okay, probably this was misleading you. Anyway, so, and this would be correct, right? Actually, this is describing that set of words. Good. How much time do I have, Moshe? 10 minutes, good. Okay, so then let's work now with non-deterministic Bücher automata. Let's do some verification with this program. Remember, this program also had infinite executions, right? So actually, how do we construct a system NBA for this program? Well, we are going again to consider all states final, right? The only thing you have to be a little bit, which is a bit annoying, is that, well, what happens with the finite executions, right? Somehow you would also like to consider to take them into account. But if you just only worry about infinite executions, you will not even see those. So the trick that is always used is to transform artificially finite terminating executions into infinite executions, but by assuming that what you do is you just stay there forever. You stay in the final state forever, right? So that's why you add a loop here and a loop there. And now this one is describing the infinite executions of the program. So now, so terminating executions model as infinite executions that stay forever in the terminal configuration. So actually, in this case, there are exactly 4 maximal executions. One where you go there and stay there forever. One where you cycle here forever. One where you go there and stay forever. And one where you go there, come back there, and stay forever. Okay, but of course, in general, there can be infinitely many, right? Now, which is, for instance, take this property, no maximal execution, none of these maximal executions, either terminating ones or the non-terminating infinite ones, visits line 3 infinitely often, right? How can we specify this? We can specify it like this by saying that, well, the violations are those that visit line 3 infinitely often, right? And now we can get a Bücher automaton for it. It's going to be like this. Okay, and now what we can do is to compute the intersection, right? So we have a system NBA, and we have a property NBA. And now how do we construct the intersection? Well, actually, for the when we were doing, recall first the NFA case, right? If I give you two NFAs for the set of executions and for the set of violations, the check that the intersection is empty takes this time, okay? Because you have to compute an NFA for the intersection, which has the size, and you have to check for emptiness of that automaton, which you can do just by applying a for search. Well, the idea is that actually here you can use the same algorithm as you use for NFAs. Probably many of you have heard that the algorithm for intersection of NBAs is not the same as for intersection of NFAs, but actually for the case in which one of the two automata has only final states, for the case in which all states are final, actually you can use exactly the same algorithm. So you could use exactly the same algorithm, and otherwise you would have to use a slightly modified algorithm that I don't want to get into, but it will give you just, you will have, instead of giving you a number of states of this number of states, you would have to put a 2 before that, right? But it is very, very similar. And then the check, you have to check for emptiness. Now this is a bit more tricky, right? Because now you cannot checking. What does it mean to check for emptiness? That the language of a Bushy automaton is empty. It is not enough to check that you can reach a final state. You have to check that you can reach a final state, and that is you can reach a final state which is in a circuit, right? Because then, you can go here and then cycle here, and then you will accept something on that run, right? So you have to check the existence of an accepting lasso. If you haven't seen this before and you think about how would you do this, probably the algorithm you will come up with is a quadratic algorithm, an algorithm which takes quadratic time in the size of the system, but actually there are algorithms which are linear, okay? The first one was described by Moshe and some other people many years ago, so it actually is Vardi. I think it's the only paper I know about you where you are the first author.
I'm not the first author.
You are not?
I'm not the last.
You are not the last, that's right. How is it? No, it's Vardi, Volper, Yanakakis, Kurkubetis, right? Kurkubetis. So it's Kurkubetis, Vardi, Volper, and Yanakakis, right? And
not even the one before the last.
Yeah, the last. Right, so you can do that in linear time, and actually you can also do it using Tarjan's algorithm for computing strongly connected components in linear time. You can also do that. Well, but the important thing is that we have the same asymptotic complexities as in the case of finite automata, right? And this is what we will have, the system NFA, the property NBA, and then this will be the product, right? Again, with the same color coding. This stands for the pair where you have this state and that color. And you can see in this case actually the only thing, notice that this automaton is deterministic, right? And then when you construct the product, actually the only thing you are doing is coloring the states here. You cannot generate more states than those, right? And now you can see that there are no accepting lassos here. The only accepting state is this one, but there is no lasso for that one, right? So the property holds, okay? Good, so no run B6 that state infinitely often, so there are no violations, property holds. Okay, and now we can check the finite weighting property, right? We have the system NBA that we had before for Lamport's algorithm, right? It will be the one we saw, but with all states final. And now we have this Büchi automaton for the property that we want to check, right? It's the idea that these are the violations. I am trying to enter the critical section, but I do not enter, right? And we see that for the property actually fails. And it fails for both processes, which you will find a bit weird, right? But these are the point at which this is a warning that when you are modeling, you have to be careful. Let's see what happens here. So you would not expect, actually what happens is that for process 1, it fails because it fails. But for process 2, actually we would not expect it to fail. Why does it fail? Well, it fails because you find this execution, right? This omega execution. This omega execution corresponds to, initially nobody is interested in entering the critical section. Both processes are outside the critical section. Then process 0 says, I am interested in getting into the critical section. It moves to T0, right? Then the other process also says, I am interested in getting into the critical section. It's process 1, right? But the idea is that this action is one that takes you, the action that takes you from here to there is one, when you are here, now you can repeat this infinitely often, okay? Now,
you can show the algorithm again, but I thought it has a weight, it will wait on the other one to change before it.
yeah, that is let's see what happens. Actually, let's see, assuming that we have enough time, it is, we have to go back right. Let's look at this, right? Okay, so the idea is that you are here, right? You are awaiting this, but look at this. So you set both set to 1, right? Okay, and now what this one is doing is checking, let's see, what's happening here, yeah. In the modeling that we had, I have to show you the modeling. The modeling that we had is that this one is checking whether the variable is 0 or it is 1, right? We are modeling this await as what is called busy waiting. So this one is checking whether, I check the value of the variable. If it is 0, then I move. If it is 1, I stay, right? So actually what is happening here is that in our modeling, because we are modeling this like this, right? We are allowing for an infinite execution where this guy is just checking here forever. This is not a real execution of the system, because this would be only a real execution of the system if this guy, at this point, would crash, right? Because this guy can set its variable to 0 at any moment. Sorry, it can check, which is the one? This guy can go here, can go here at any moment, right? And then this one will move. No, sorry, it can, I am now a bit lost.
Basically, you let, it's an unfair execution.
It is an unfair execution, that's the point I want to reach, right? It is unfair in the sense that this one is just sitting there, and even though it could at any moment do something, right, it doesn't do it.
Because it's never scheduled.
Because it's never scheduled, right. Okay, so this is actually a property that, so you see that the property fails, but it fails not because the algorithm is incorrect, but because of the way you model your algorithm, okay? So how can you take care of that? So the important thing is that we have to take care of that, and there are different ways of doing that, right? The typical, the way is always to introduce a fairness assumption, right? And one fairness assumption that you can introduce in this case, which one you need in each case, it may be a different one. In this case, it is enough to assume that both processes execute infinitely many actions. If you look at your system, you will see that wherever a process is, it can always execute one action, right? So what we are going to assume is that the processes execute infinitely many actions, right? And then the violations are going to be the fair full executions, right? And how can you do that? Well, you can represent the fairness condition by enriching the notion of configuration, right? You do not only say, I have reached this configuration, but you also say which process made a move in order to reach this configuration. And then if you say which are the sets of configurations where the last process that made a move was process 0 or was process 1, these are these two sets, right? Then you can describe the violations of fair finite waiting like this, right? You are going to say it is the set of executions which contain infinitely many moves of each process intersected with the set that violate the property, right? And another way of writing this is like this. But the point that you are starting to see now is, well, this is starting to get a bit difficult to parse, right? So this is now a bit complicated, this expression, so we would like to have a better way of specifying these things. And this is nothing but what Orna has shown you in the last lecture, right? Temporal logic. But now we are faced with the problem of going from temporal logic to automata. Okay, we will have to be able to go from temporal logic to automata, and that will be actually what we will be doing in the next lectures. And time to stop, right?
Thank you.
Thank you.